All right, we just finished up chapter 1 talking about the anatomy and physiology of the heart. So now we're going to move on to chapter 2 where we're going to talk about the electrophysiology of the heart. I just want to point out that as you go through this course, you'll notice that each chapter builds off on the one before. So if you don't fully understand chapter 1, make sure you review it before moving on to chapter 2 and so forth. If you don't understand chapter 2, make sure you review it before you go on to chapter 3. Okay? So, chapter 2, the electrophysiology of the heart. So, cardiac cells, we just got finished talking about this in chapter 1, that are at rest are electrically negative on the inside compared to the outside of the cell. So if I have a cardiac cell and it is at rest, it has a negative charge. The movement of a charged particle, this is going to be a positive charge, of ions of sodium and potassium cause changes that can be picked up by sensors on the skin. These changes can then be printed out on an EKG. That's a lot of information right there in your first slide. So again, your cardiac cell at rest has a negative charge. But when a cardiac cell has charged particles of sodium and potassium, they can cause changes and become positive and pick up the sensors on your skin. That leads into depolarization and repolarization. Just new terminology put with something you've already known, which is relaxation and contraction. So, a negatively charged resting cardiac cell is known as polarized or polarization, meaning there's nothing going on. It is polarized. It has a negative charge and it is at rest. This is when your sodium ions are primarily on the outside of the cells and your potassium ions are primarily on the inside of the cells. Both of the ions are going to carry a positive electrical charge, but depending where they are in the cell determines what the cell's charge is going to be. So if I have sodium ions that are positive on the outside of the cell, and I have potassium ions that are positive on the inside of the cell, they are both carrying a positive charge, but my cell is going to be at rest and is going to be negative. The potassium charge has a weaker charge. So sodium is going to be stronger than your potassium charge. Again, a lot of information. So at rest, there's nothing going on with my cell. Nothing's happening. It is polarized and it is negative. Sodium is on the outside. Potassium is on the inside. Both ions, sodium and potassium, carry a positive charge. When cardiac cells are stimulated by an electrical impulse, this is like electricity. This is like a spark, a fire. That impulse, large amounts of sodium from the outside are now going to rush into the inside, and the potassium on the inside is going to leak out. This is the electricity that is discharged. So I want you to think about batteries. When you need something to work and it needs 2 AA batteries, you are to put a negative next to a positive, and then whatever toy you're trying to get to work is going to work. But if you were to put a positive next to a positive, the batteries are going to retract. They're going to pull away from each other because you can't put a positive with a positive. That's what's happening here with our cardiac cells. At rest, my cardiac cell has a negative charge. Sodium is on the outside, potassium is on the inside. But when that cell is stimulated by electrical impulses, the sodium is going to rush in and some of the potassium is going to get out because both the sodium and the potassium have positive charges and they cannot be next to each other inside the cell. When this happens, the electricity is then discharged and my cell becomes positive. This is called depolarization. The electrical wave courses from cell to cell, and the electrical charge spreads throughout the heart. So I want you to think about this. Think about a firework. When you go to light a firework, you're going to light the wick at the end of the firework, and you're going to get a spark. Is that spark, that ignition, that electrical impulse, is it going to stay right there at the end of the wick and go nowhere? I hope not, unless you have a dud. It's instead going to travel up the wick and eventually shoot off that firework into the air. That's what's happening with your cardiac cells. The cardiac cell is going to be initiated by an electrical stimulus, an electrical impulse. Once that stimulus is activated, once you light the end of the wick, the sodium cells are going to rush in, potassium cells are going to rush out, and they are going to travel up the wick. So when one cell becomes positively charged and touches another cell that is negative, it's going to cause that negative cell to become positive, and it's going to lose its charge. It's going to give it away and go down the line. So each cell that touches another cell will get the electrical impulse and become a positive charge. But that impulse is not going to stay with that one cell. It's going to travel to another cell, like that firework. So that cell that originally had it has now become relaxed and has given its charge to another cell that has contracted, which is called depolarization. Another way to think of this is if you ever plug in something into the wall and you get a small electrical shock, your first reaction is to pull your hand away from the wall very quickly. Ow, it hurt, right? That is depolarization. So when the electrical current hits your fingers tighten up and you immediately react by pulling away. That's the same thing that's going on with these cardiac cells, is they are becoming stimulated with electrical impulses, and as soon as it touches them, they want to get rid of that electrical current and give it to the next cell that they touch, just like when you touch that outlet. And to remember that if I am a negative cell at rest, my sodium is on the outside and my potassium is on the inside, and I have negative charge for the cell. But the sodium and the potassium have positive charges. And when the cell becomes stimulated from another electrical cell, when that stimulation occurs, that conduction, the electricity is being passed on to another cell. The sodium is rushing in and it's positive, rubbing up against your potassium, which is positive, and we know you cannot have a positive with a positive inside a cell. The potassium is going to leak out. This causes the spark, the ignition at the end of the firework, that is then going to travel and carry that signal from cell to cell to cell. So the cell may be depolarized with the electrical charge. It gives it away to the next cell, and that original cell becomes relaxed and repolarized. It goes back to its negative charge. During cell recovery, this is your repolarization. During cell recovery, sodium and potassium ions are shifted back to their original places. This is accomplished by the way of the sodium-potassium pump, an active transport system. This is called repolarization. So if I have a negative cell at rest, it's polarized. Sodium on the outside, potassium on the inside. It's a negative charge. I am stimulated by an electrical impulse from another cell. My sodium is going to rush in and my potassium is going to rush out, and then I am going to have a positive charge. Well, now I'm going to give that electrical charge to another cell and give it away, and then So then I'm going to become polarized because I'm going back to my original negative charge, which is repolarization. So I start off negative, I am polarized. I become positive, I am depolarized, and I need to get back to being a negative charge, and I then become repolarized. Depolarized is going to be the contraction, and repolarized is going to be relaxation. Polarized is going to be a negative charge and there's nothing going on. So here in this image in 2-1, you'll see that it just puts it into a visual for you. You'll see in the first image is a polarized cell where the electricity is negative on the inside compared to the outside. So even though you see this negative charge on the inside and this positive charge on the outside, it's important to understand that my sodium and my potassium both have positive charges, and it depends where they're at in the cell. So if my sodium is rushing into the cell, I am going to give a positive charge. But if my sodium is rushing out, I am going to have a negative charge. That positive charge is depolarization, contraction, and the negative charge is repolarization, relaxation. So, and then in the second one, you'll see that depolarization occurs when sodium rushes into the cell, resulting in a positive electrical charge and the start of an electrical current. It goes on to your conduction. Conduction is electricity. So that is passing the charge from one cell to the next. I'm conducting it. I am telling cell 1 to take this positive charge to cell cell 2. 2, take it to 3. 3, take it to cell 4, and so forth. I am conducting the pathway. So the conduction occurs when positive ions move to adjacent cells. I also like to give the example of a ball ricocheting. If you have a line of balls, let's say they're all lined up, basketballs, there's 10 of them, and you take the first basketball and roll that basketball to hit the entire line of balls, the first basketball hits the second ball, which hits the third, which hits the fourth, and so forth. But that first basketball, does it keep on rolling? It stops. It repolarizes. It goes back to being still, and it just goes along the line just like that. So that is your conduction. When that ball becomes still and repolarizes and relaxes, this is called the sodium-potassium pump. It moves the potassium into the cell and sodium out. And then repolarization is when the cell has completely returned to its resting negative charge. All right, depolarization and repolarization. Myocardium's electrical stimuli. So again, remember, myocardium is the middle layer, tissue layer of the heart. Myocardium. It is also the thickest muscle layer. This is where contraction and relaxation should be the mechanical response. What does mechanical response mean? Meaning if I electrocute myself by plugging something into the wall, I'm immediately going to pull my hand back and my hand's going to go back to normal. It's a mechanical response to that electrical shock. So it's a response to the electrical shock. So contraction and relaxation should be the mechanical response. Depolarization should result in the heart muscle to contract, and repolarization should result in relaxation. The electrical stimulus precedes the mechanical response, meaning there will be no heartbeat without first having depolarization. There could be a mechanical problem making your myocardium incapable of pumping. So for instance, let's say you're getting electrocuted by the plug, but you do not pull your hand away because you do not have feeling, because maybe you have some scar tissue from a burn right there. So you don't feel that electrical impulse. This can happen with your heart. There could be a mechanical problem making the middle tissue layer incapable of pumping. The electrical stimulus proceeds, but does not guarantee a mechanical response. So I'm going to look at your action potential. So your action potential is, it shows a graph basically of your action. So everything we just discussed, we're going to put into a chart. So if I am polarized and I have a negative charge and I am at rest, I am stage 4 or phase 4 of your action potential. Again, phase 4 is when your cardiac cell is at rest. You have a negative charge with a resting transmembrane potential of negative 90 millivolts. And the flat line is going to indicate electrical silence. It will all make sense in the next few slides. The next phase is phase 0. Here, I'm going to have a cardiac cell that is stimulated. What do I mean by stimulated? An electrical current has stimulated that cardiac cell, causing it to be a positive charge. The sodium is rushing in, potassium is rushing out. This is depolarization. What is depolarization? Contraction. This corresponds with a QRS complex on an EKG. The spiked waveform represents depolarization of ventricular myocardium. So that spike that you see on an EKG rhythm is going to represent depolarization. Depolarization is contraction. It is a mechanical response of the electrical current being conducted from your cardiac cells. That the cell is a positive charge, the sodium is rushing in and the potassium is rushing out. And it is going to contract the ventricle's middle tissue layer. You remember your ventricles are your bottom chambers. Phase 1 and 2, this is going to be early repolarization. This is important to know because it doesn't show you on that diagram we just looked at. So make sure you highlight, underline, circle, put a star by it, whatever you need to do to remember. When calcium is released, it's going to result in contraction. Again, what is contraction? Depolarization. So in phases 1 and 2, this is early repolarization, and it is also when calcium is released, resulting in ventricular contraction. It corresponds with the ST segment of the EKG, the flat line, and phase 2 is also called the plateau phase, where the waveform levels off here. So phases 1 and 2 of your action potential is repolarization, early repolarization. This is where calcium is released, and it corresponds with your ST segment of the EKG. That's coming up in the next few slides. The flat line on the EKG that follows the QRS complex. Phase 2 is called the plateau phase. This is where the waveforms level off. Phase 3 is rapid repolarization. Sodium and potassium return to their normal places. That's your sodium-potassium pump. It corresponds with the T wave of the EKG. Broad, rounded wave that follows the ST segment represents ventricular repolarization. Alright, so here you are. I'm going to stick with green. So we notice we have phase 4 right here. And where is phase 4 located? It is located on a flat line. I want you to imagine this as a timeline. Positive above the line, negative below. My phase 4, is there anything happening here? Am I more positive than negative or more negative than positive? I'm neither. I'm neutral, which means I am polarized. There is nothing going on. Okay? But then look at phase 0. What happened here? I shot all the way up to 20 millivolts. And I was originally at a negative 90 millivolts. This is going to represent my QRS. Okay? When I shoot all the way up, I become positive, meaning my cell now has a positive charge. A positive charge is indicative of depolarization, which is contraction of the cell. But does that contraction stay right there in that cell? No, it's going to pass it on to somebody else. So when that contraction hits another cardiac cell, we're going to go into early repolarization, phases 1 and 2. And then we're going to go into rapid. It's like a roller coaster. It drops down super fast. Repolarization, my sodium potassium pump. And I'm going to wind up repolarized. Okay? So this mimics your EKG rhythm that prints out. This is what we're looking at when we look at your heart and the rhythm prints out. Your QRS is going to represent depolarization, and your ST segment and T wave are going to represent early and rapid repolarization. Again, depolarization is contraction, repolarization is relaxation. And when I'm polarized, I am at a negative 90 millivolts. My cell has a negative charge. I'm polarized. And when I become depolarized, I become positive, and I have an electrical stimulus that I'm then going to get rid of and go into early repolarization and rapid repolarization. So let's talk about, let's say there's a second stimulus coming. So let's say you have cell A and cell B. Okay, cell A gets an electrical impulse, gets this spark at the end of the wick of the firework, and it wants to give it to cell B, so cell B can give it to C, and C can give it to D, and so forth. Well, what if cell A fires off and gets another impulse right after and sends that one off as well? So now you have two sparks coming down the line, right back to back. When will that spark accept a second spark in its cell, and its electrical charged, positive charged cell? So we have three phases. Absolute, meaning if I'm in the absolute phase, location of the heart, I will not take a second stimulus that can cause depolarization. If I am in a relative phase, that stimulus has to be strong for me to take it and cause depolarization. But if I am in the supernormal phase, even a weak stimulus can cause depolarization. This is your cardiac cell, and it is hyper. So if you look at the chart here, you'll learn here in a minute that this first wave is P. This is your PR segment. Here is your QRS complex. Here is your QT segment, if I said that right. And then here is your T wave. Here is your baseline. Here is your baseline. If I wanted to label my action potential, I would have 4 here, which is polarized, 4 here, which is depolarized. I would have phase 0 here, phase 1 and 2 here, and then phase 3 here. So this is depolarization, early repolarization, rapid repolarization, and polarized. If I have a spark, let's give it a little round circle. If I have a spark here in cell 2, and cell 1 has another spark coming, this spark cannot come into this box at all. Absolutely will not take a second charge. But if that spark is weak, and I am now over here, I might take that spark. The problem is if that spark catches up to my first spark, it can cause me to go back into depolarization. And then if my spark is over here, I most definitely will take whatever sparks come my way. So, absolute phase, I will absolutely not take a second cell in my box. Relative phase, if it's weak enough, I might let you in because you're not strong enough to pull me back into my absolute box. And whether I'm weak or strong, if you try to come into my supernormal box when I'm in there, I'm going to let you in. So another way to remember this is Halloween, right? Candy. Absolute is your stranger. Are you going to take candy from the stranger? Absolutely not. But what if that person is a relative? It's your mom, your dad, your cousin, your aunt, your uncle. Are you going to take candy from them? Maybe, but only if they're weak, right? If it's a weak candy. Maybe it's not as high in calories. But super normal, this is your super hyper friend. Are they going to take candy from the stranger? Yes. They're going to eat it from anybody and they're going to get in trouble, right? So, if I am a cardiac cell and I have a negative charge, I am polarized, meaning my sodium is on the outside and my potassium is on the inside. But when my charge becomes positive in phase 0 at the QRS, that means I am carrying a spark, an impulse electricity. I am in the absolute phase in between my QRS and my T wave. So if another spark comes up behind me, it cannot come while I'm in this area of the rhythm. But if I go in, my spark goes into the T wave and I am in the relative box. If that spark that's trying to get in, the second spark that's coming is trying to get in and is weak, I just might take that charge and add it to my box. And then if I am in the super normal friend, my super hyper friend, they're going to take candy from anywhere. I'm definitely going to take that second spark regardless of it being weak or strong. The problem is when you have an electrical current or a charged cell coming into that area of the heart, it can cause it to go back into depolarization without being able to repolarize before it depolarizes. So the whole cycle is you're going to start off negative and you want to become positive and you want to end up negative. You don't want to start off negative, become positive, stay positive, stay positive, stay positive, because your heart never gets to relax and return to its original polarized state. Your heartbeat becomes fast and this can lead you into a heart attack. Okay, so now let's talk about the waves. So I just showed you your P, your QRS, and your T on the rhythm. But in more specifically, the P wave is going to show us the atrial depolarization of the heart. So your atrium, the top chambers, are depolarizing, meaning they're contracting. And remember, everything is simultaneous in the heart. So when the top chambers contract, the bottom chambers relax. So if my P wave is showing the contraction of my atrial, my ventricles at this moment are relaxing, which are your bottom chambers. I want you to ignore the name of this next one. I find that it's very confusing. Atrial repolarization. So once we go from a polarized negative charged cell to depolarized, a positive charged cell, we want to repolarize and go back to negative. This is atrial repolarization, but you cannot usually see it, and it is usually occurs simultaneously with the QRS. Your QRS complex is ventricular depolarization, and it is a normal QRS. It's spiked in appearance, consisting of one or more deflections from the baseline. Whenever you see deflections, I want you to think of pictures. That's what it's talking about. So ventricular depolarization is your bottom chambers, your ventricles. They are depolarized, meaning they have a positive charge. The sodium is going in and the potassium is coming out, and they are contracting. The T wave is when your ventricular repolarization, which is when your ventricles are then going to go back to the polarized state called repolarization. A normal T wave is broad and rounded. The U wave, this will be the only time we talk about it in EKG 1. It'll come back at you to bite you in EKG 2, so don't forget. Your U wave is called late ventricular repolarization. So maybe that heartbeat is a little bit slower than normal and it came late. This is your U wave. It's normally not seen, and it should be shallow and rounded, and it will look a lot like the T wave. So here's an image. And I want you to notice, first of all, the spikes. So you'll see a spike here, a spike here, and a spike here. These spikes are different heartbeats. So in this specific image, we are looking at 3 heartbeats, okay? And I want you to look at the line in between each of these heartbeats. This line in between is called your baseline, or in other words, your flat line. But we have 2 additional lines in between our waves. These 2 are your segments, and I did say that wrong earlier. It is your ST segment, not your QT segment. So at your baseline, we're isoelectric. We are action potential phase 4. We're negative charge. There is nothing going on. But then you notice we have our P wave, which is my atrial depolarization. And then we have our PR segment, which is in between my P and my R wave. From there, we go up to phase 0, which is a positive 20 millivolts. And gives my cell a positive charge. And then we're going to come back down in phases 1 to 2 of your action potential, which is early repolarization, meaning sodium is getting back out of the cell and your potassium is getting back in. And I am going to go through rapid repolarization when I am at my original spot. Here is when you rarely see, so then you have your T wave, and then here is when you rarely see that U wave, and that is late repolarization. Okay, so one thing to notice is your rhythms are your alphabet. So you have P, Q, R, S, T, and U. This is giving you a visual of what it looks like when there is a contraction and relaxation going on. So in image 1, you'll see here we are contracting and it is spreading out, but it's not completely filled. So this is your cardiac cells sending their impulse. We're ricocheting, we're giving our charge to the next charge, to the next, to the next, to eventually charge the entire atrium, which is depolarization and causing it to contract. Then atrial depolarization is complete. We're completely highlighted. And I am now going to send that electrical signal down into my ventricles. So now my ventricles are starting to contract while my atrium is relaxing. Notice my ventricles are completely highlighted now, so they are in full contraction. And after that contraction has completed, I then start to repolarize. Early repolarization, rapid repolarization. So for each PQRS-T sequence is one heartbeat. Your PR segment is the flat line between your P wave and your QRS, and your ST segment is the flat line between your QRS complex and your T wave. The baseline is a flat line between the T wave of one beat and the P wave of the next beat, also called your isoelectric line, meaning it's equal on both sides. We're at a negative charge and there's nothing happened. We're polarized. So if we have P, QRS, and T, and here's my baseline, and here comes another P, QRS, and T, and then here comes another baseline, P, QRS, and T baseline. So my flat line in between my T and my P is called my baseline. And then we can label P, Q, R, S, and so forth. T, P, and T. Alright, atrial contraction occurs during P wave and PR segment. Ventricular contraction occurs during the QRS and the ST segment. So remember, contraction is depolarization. So atrial depolarization contraction, a positive charge, occurs during the P wave and the PR segment. And then your ventricular contraction occurs during the QRS and the ST segment. So I'm going to just do a couple of these practices with you. The following strips are to practice identifying the P, QRS, and T. P waves usually precede the QRS, meaning they come before. And to find the QRS, you're going to look for that P wave. The QRS complex is mostly identified structure on the strip because it is spiked. So here we're going to see your QRS right here, and here is your T, and here is your P wave hidden. Okay, so you notice it's not that perfect looking rhythm that we've been talking about. Again, here is my baseline, here is my P, here is my QRS, and my T. Baseline, P, it's hidden, and here is my QRS. Alright, second strip, this one's easier. Notice the spike, here's a spike, and there's a spike. That indicates my QRS. What comes before Q? P, that is this first wave, and what comes after S? T. Now, look at the remaining waves. All four of these, do they look more like my P or my T? Your answer should be P. So the rest of these are P's only. What happens if I see a P wave? I am seeing atrial depolarization. Am I seeing ventricle depolarization? Am I seeing atrial repolarization? No. So is my electrical spark getting through to the myocardium throughout the heart from all the way down to the ventricles? No, there's some kind of damage somewhere. Something's wrong. Okay. Again, look for the spikes. Oh, I messed that up. Let's see. Okay. Here's a spike, QRS. Here's another spike, QRS. And here's another spike, QRS. The wave in front of my QRS is P, alphabet, and the wave after is a T. And this line in between is my baseline. Now don't forget, your lines in between here is your PR, and your line in between here, I don't know why I can't remember, is your ST segment. So here's my P, T, baseline, P and T. And of course, these circled spikes are my Q or S's. Okay, so if you look here, I do not see a P wave, but I see my Q or S, and I see my T wave, Q or S, and my T wave, and so forth. And then the last one, I am isoelectric, I am flatlined, I am a baseline. Now, let's look more at your Q or S complex. Your Q wave has a negative deflection. This is very important to know. So your Q wave has a negative deflection. Again, what's deflection mean? Picture that occurs before a positive deflection. There can only be one, and if present, it must be the first wave of the Q or S complex. Your R wave is any positive deflection. Again, deflection is picture, and you can have more than one. If you have more than one R wave, the second one is called your R prime. So again, very important, your Q wave has a negative deflection on that number line. There can only be one. Your R wave has a positive deflection, and there can be more than one. The second one is called R prime. Your S wave is negative, just like your Q, and it's going to follow the R. And then you can have what's called a QS wave, is where you have a negative deflection with no positive, meaning no R. Okay, so for example, here we have a positive deflection, so it is just a R wave. But here we have a negative deflection with no positive, which makes it a QS. Here we have a negative deflection and then a positive, which makes it a QR. And then we have a negative and then, a positive, then a negative, which makes it an RS. So notice the S, it's not a Q because it's coming after the R. So it is an S. But if it was a negative deflection before the R, it would be a Q. So here you see your negative deflection is Q, positive R, negative is S. And then you have your positive deflection is R, negative is S, and your second positive deflection is R prime. So remember, if you are imagining this as a number line, positive is up and negative is below. So we're going to name these real quick. This one we just did, it's an R. Here's a QS. Here is a QR. Here we have a RS. Here we have a Q, R, and S. And I can't see the other one, which looks like an R, an S, and an R prime. So cardiac conduction system, so we're moving on to your conduction system, is the pathway of specialized cells that create and conduct electrical impulses that tell the heart when to pump. So we know that when blood fills up the chambers of the heart from chapter 1, it causes the valve doors to open, that one-way door, right? But once those doors are open, how does the heart muscle, how does that atrium squeeze the rest of the blood out? That's where your cardiac cells come. They are going to cause that electrical signal so that when that cell with an electrical charge, positive, touches your muscle, it causes it to tighten up and to contract to get away from that electrical signal. So a pathway of specialized cells, these are your cardiac cells that create and conduct the electrical impulses that tell the heart when to pump. The area of the conduction system that initiates the impulse is called your pacemaker. Very important to know. The area of the conduction system that initiates the impulses is called the pacemaker. So, This is your conduction system, okay? So here we see right atrium, left atrium, right ventricle, and left ventricle. Right here in the middle is my septum. Here is my superior and inferior vena cava, my aorta, and my pulmonary valve, pulmonary artery, and my pulmonary veins. All of that here from chapter 1. So, who is my pacemaker of the heart? Sinus node. My sinus node is going to send that electrical spark from my sinus node down into the internodal tracts and across into my interatrial tracts. Okay? From there, my impulses need to reach the AV node, which is right here. Okay? And then my AV node is then going to send those cells, that electrical impulse, to the bundle of His, which then branches off into right and left branches and end up on these little root systems down here known as your Purkinje fibers. So what is a conduction pathway? We're going to start at the sinus node. We're going to go to your interatrial tracts. So if I start in the right atrium, I need to get to the left atrium. How do I get there? I'm going to go through your interatrial tracts to the atrium, and then I need to get to the AV node, atrioventricular node, through your internodal tracts to your AV node. There, I'm going to then go to the bundle of His, and I'm going to go into right and left sides, your bundle branches, and I'm going to end at the Purkinje fibers by contracting my ventricles. So what type of cells do we have? What kind of cardiac cells do we have? We have automaticity, conductivity, excitability, and contractility. Your automaticity is the ability to create an impulse without an outside stimulus. So my cells in my original pacemaker, my sinus node, are automatic. They initiate, they create that spark right there. The conductivity is that conductive line. I'm giving my spark, my impulse from one cell to the next. I'm not hanging on, and I did not create it. It was just passed to me, so I'm passing it to you. I'm paying it forward. That's your conductivity cells. The ability to conduct an impulse to its neighboring cells. Excitability is the ability to depolarize, meaning I am excited, I am waiting to get that electrical charge so I can get the spark and get that positivity. I'm excitable. And then contractible is the ability to contract when, that's your mechanical response, right? The contractility, the muscle contracts when it is touched with the electrical charge. It is a mechanical response. All right, so cardiac cells, automaticity, conductivity, excitability are your electrical characteristics, but your contractility is mechanical. Your sinus node is the normal pacemaker of the heart, and there are other cardiac cells can become the pacemaker only if the sinus node fails. The other pacemakers of the heart is your AV and your ventricles. So your sinus node, known as the heart's normal pacemaker, is an inherent rate of 60 to 100 beats per minute. You have to know this. This is where I would start making a note card if I were you, to start gathering, or even just a blank copy paper. Start gathering this information in one spot and use it as a guide for the rest of EKG 1 and EKG 2, because this is information that you're going to be constantly going back and looking for until you memorize it. Your sinus node has an inherent rate, meaning it can send an impulse that will cause your heart to beat 60 to 100 beats per minute. Your AV junction is the backup pacemaker. So let's say my sinus node's not working, AV needs to start making my impulses. That rate can only be 40 to 60 beats per minute. It's going to be a slower rate. And then my ventricles is going to be a lower backup pacemaker, and the inherent rate is 20 to 40 beats per minute. So If my sinus node fails, who's going to work? AV. But can AV work as fast as sinus? No. What if my AV fails? Who's going to pick up the slack? Ventricles. Can my ventricles work as hard as my AV and my sinus? No. So the original pacemaker of the heart is your sinus node. But if it fails and your AV is sending off the impulses, it now becomes the pacemaker of the heart. And then if my AV fails and my ventricle has to start sending impulses, my ventricles become the pacemaker of the heart. The fastest pacemaker at any given moment is the one in control. The lower pacemaker serves as a backup and are inhibited from firing as long as some other pacemaker is faster. What does inhibited mean? It means to prevent. So even though my AV and my ventricles are capable of sending off impulses, they are inhibited, they are stopped because the sinus node is sending off the original pacemaker impulses. But if my pacemaker fails, my AV now becomes the pacemaker of the heart. Or if my AV fails, my ventricles become the pacemaker of the heart. Conduction variation. So a normal conduction of cardiac impulses is dependent on the health of each part of the system. Failure of any part of the system necessitates a variation. This is just going to give you an image of what we just talked about. So if you were to put it in simple terms, your sinus node is the original pacemaker of the heart, sends the impulse to my atrium through the interatrial tracts, which then send my impulse through the internodal tracts to my AV junction. My AV junction then sends it to my ventricles. What does the atrium look like on an EKG? The P wave. P. And what does my ventricles look like on an EKG rhythm? The QRS complex. So let's say sinus node, it's not working. Atrium, it's also not working. Meaning since there's no impulse on my sinus node getting to the interatrial tracts, my AV junction is then going to have to fire off at a slower rate, 40 to 60 minutes. But notice when it fires, it goes in both directions, which means my atrium are going to get depolarized. But what if sinus node's not working, atrium doesn't get depolarized, and my AV junction is not working? The only one working is my ventricles, therefore I will only see a QRS. And will my atrium get polarized? No. Which means if a muscle does not get oxygen, it's eventually going to turn black. So if you were to stick a rubber band on your finger, at first your finger is going to turn, it might turn white or red, then it's going to turn blue, and then it's going to turn black. And eventually, can you save that finger after taking off that rubber band and it's turned black? No, you're going to have it amputated. That's what's going on here. So if my ventricles is the pacemaker of the heart, my atrium is not getting oxygen pushed to it, which means it is dying, and eventually we will not be able to save it. Okay? Here you see your sinus node is working, and your atrium is delivering the conduction cells, but we're blocked. Maybe there's some plaque in the heart. Maybe there's a block in my arteries. It's clotted. Maybe there's a blood clot. Who knows? But for some reason, my impulse is not getting through. It is being blocked. So my AV is going to instead send an impulse. But remember, AV can also send to my atrium, and it's going to go around that block. Now we have what's called, you're going to learn two types of impulses, which is escape and usurpation. Escape is your predominant pacemaker, which slows dramatically after it fails. The lower pacemaker takes over at a slower rate. An escape beat is any beat that comes in after a pause that's longer than the normal heartbeat to heartbeat cycle, which is called your R to R interval. This is important to know. So if we have a P, Q, R, S, and T baseline, P, Q, R, S, and T, this is called the R of my QRS. And the distance in between my two QRSs, my two beats, is known as my R to R interval. Your escape beats are your lifesavers. So notice beat 1, beat 2, beat 3, beat 4, and beat 5. Look how spread out they become. So for beat 1, 2, and 3, I'm looking almost normal. I'm missing my P waves. But then I have a long pause. And now I have an escape crazy looking beat. So think about over here, this is my SA node. I'm getting beats, they're going through, they're good, and they're on time. But then SA node didn't send a beat. AV node is waiting. AV node didn't get the beat, so my ventricles are going to send off an escape beat, which is going to take slower, causing my pause. And I'm going to get this crazy looking QRS. That is your escape beat coming from a lower pacemaker. Usurpation is irritability. That is when your lower pacemaker takes control and fires at an accelerated rate, stealing control from the predominant pacemaker. So this is, we're talking about, again, your refractory and absolute and super normal refractory periods. So when a lower pacemaker takes control and fires a fast impulse, stealing control from that predominant pacemaker, it is going to cause the rhythm to be fast, meaning it's going to keep on depolarizing at a faster rate. So here you'll see a normal beat and a normal beat, and then bam, fast beat, faster, 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 faster. This is your usurpation. All right. So the conduction variations, proper function of the conduction system results in a heart rhythm. The pattern of successive depolarizations originate from the sinus node. So we know that that's your pacemaker of the heart. Abnormality, so a rhythm that does not look normal, for example, the escape or the usurpation, that is going to be called an abnormal arrhythmia. So I always think of arrhythmia, abnormal, normal rhythm, arrhythmia, abnormal. They can prove to be harmful or fatal if not treated properly. So we're going to talk about graph paper. We have about 2 more sections to discuss. Your graph paper is divided into small blocks each. So here's a small block. Each side of it is 1 millimeter in height and in width. Okay. The dark lines represent the 5th box subdivided on the paper vertically and horizontally. You need to know that vertically is going to be measuring your amplitude, and horizontally measures time, which is your intervals. Alright, so here you'll see your dark lines, which separate your big boxes from your little boxes. And you'll notice that you have even darker lines that separate, oh no, your 5 boxes. So it moved the screen and I can't go back when I am doing these recordings. So I'm just going to go ahead and draw it. So if you have 5 big boxes, that's 1, 2, 3, 4, and 5. This is going to equal out to 1 second. Okay. If you have just one of these big boxes, this is going to equal out to 20 seconds. 0.20. And then if you have one little bitty box, this is going to equal out to 0.7 0.04 seconds. This is going to be measuring your time horizontally intervals. So a 12 lead is the printout of a heart's electrical activity viewed from 12 different angles and 12 different leads. I'm just going to introduce you to 12 leads here, but we're going to go into more in depth in ch02 for this. The lead is the electrocardiographic picture of the heart's electrical activity. A rhythm strip, this is the printout of 1 and 2 leads at a time to access the heart rhythm. It is recorded on a special paper about 3 to 5 inches wide and is a 6 to 12 second strip, which is usually obtained and interpreted. So on image A, this is just one view of the heart, but image B, you'll see 2 views of the heart. Now it's the same heart at the same time, the same heartbeat, but notice that the different views I can see better in the second view than I can in the first view, which is why we do a 12 lead EKG. So what is the benefit of double leads? Both leads show the same rhythm, they just view 2 different angles. Therefore, both leads have the same rhythm, the same interval, and the same heart rate. 2 leads provide twice the chance of identifying the rhythm. For example, P waves may not be visible in one lead, but are very clear in the other. Having 2 leads show how the same rhythm can look different in different leads. So here you'll notice your 12 lead rhythm. Here's leads 1, lead 2, lead 3, and so forth. AVR, AVL, AVF, V1, V2, V3, V4, V5, V6. And then you'll notice that this should be lead 2 at the bottom. Lead 2 goes all the way across the whole length of that 6-second strip. How do you measure these? So we know now that 5 big boxes is going to be 1 second, 1 big box is 20 seconds, and 1 little bitty box is 0.4 seconds. So we're going to measure across, and we're going to measure in between my P, my QRS, and my T. These measurements allow the determination of the heart's efficiency at conducting. Remember, conducting is electrical. From cell to cell, the electricity being handed over, impulses down the pathway. This is again one for your note cards. So I already said your SA node, your AV node, and your ventricles should be on there. Your SA node is 60 to 100 beats per minute. Your AV node is 40 to 60 beats per minute, and your ventricles is 20 to 40 beats per minute. Now you would add on to your note sheet that your PR interval measures the time of the impulse gets from the atria to the ventricles. Remember, your atrial is your top chambers, your ventricles is your bottom chambers. And the normal PR interval should be between 0.12 and 0.20. You're going to measure from the beginning of the P wave to the beginning of the QRS. How do you know where the beginning and the end of these waves are? It's what is their deflection on the baseline. Is it positive or negative? Once you see that deflection change, that's the beginning and the end of the measurements. So for my PR interval on your notes, you should be writing PR interval is 0.12 to 0.20, and it is measured from the beginning of the P wave to the beginning of the QRS. The QRS is going to measure the time that depolarization occurs. So a normal QRS needs to be less than 0.12 seconds. It is measured from the beginning of the QRS to the end of the QRS. And then your QT interval measures depolarization and repolarization time of the ventricles. This measure is done from the beginning of the QRS to the end of the T wave. This measurement should be less than or equal to 1/2 the distance between successive QRSs complexes at heart rates between 60 and 100 beats. So we're going to look at 3 measurements: your PR, your QRS, and your QT. So again, my PR interval is from the beginning of my P wave to the beginning of my QRS. How can I tell where it begins? When does the baseline change? That's how I can tell. My PR interval needs to be between 0.12 and 0.20. I could be wrong. I have to double check that. My QRS is going to be from the beginning of my QRS to the end of my QRS. Here, I want it to be less than 0.12 seconds when I do my measurements. And then my QT is going to be from the beginning of the QRS to the end of the T. And remember, this needs to be half or less than or equal to my R to R interval. All right, this is summing it up for you. So when you're determining the intervals on the enlarged rhythm strip that follow your PR interval, you're going to count the number of small boxes in between the beginning of the P wave and the beginning of the QRS, and then you're going to multiply by 0.04. For your QRS, count the number of small boxes between the beginning and the end of your QRS complex, multiply by 0.04. And QT, you're going to count the number of small blocks between the beginning of the QRS and the end of the T and multiply by 0.04 seconds. So for example, I'm going to go ahead and do this first one for you. Let's see, I can't. Okay, so to measure my PR interval, I need to measure from the beginning of my P wave. Notice, where does the baseline change? To the beginning of my QRS. Where does the QRS change? I'm going to count the boxes in between. I see 3 boxes. 3 times 4 is 12. Is my PR interval in between 0.12 and 0.20 seconds? Yes. QRS is from the beginning of my QRS to the end of my QRS. Beginning to end. How many boxes are in between? 2. What's 2 times 4? 8. 0.8 seconds. Okay. Now we need to measure my QT. That is from the beginning of the QRS to the end of my T. 1, 2, 3, 4, 5. I have 6 little boxes, and right, 6. And you know, a lot of times I won't multiply QT. I guess it depends on you. Just want to double check my math because I am tired. I don't trust my math skills right now. So if I were to multiply those, so I got 6 boxes here. 6 times 4 is 24 is what I got for my QT. But remember, my QT needs to be half the distance of my R to R. So my R to R interval, which is your spikes right here, I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I got 15 boxes. So 15 times 0.04 gives me 0.60 seconds. And the question is 0.25 seconds. This is supposed to be an S. Less than or half than less than 60 seconds, and it is. And like I said, I don't always calculate this. I'll just look at the numbers. So if I have 15 small boxes and I have 6 small boxes, I can determine that 6 is about less than half of the 15 boxes. Okay, so let's do the second practice. The PR is the beginning of the P wave to the beginning of the QRS. I've got 3 boxes. 3 times 4 is 12. QRS is the beginning of the QRS to the end of that QRS. 1, 2, 3.5, I would say. Again, so that would be 0.12. And then my QT, so remember we want to go to the beginning of the QRS to the end of the T. Now this one, notice, when does that T end? It ends when we get back to the baseline. So where does that change? Right here. So I'm going to count. That's 3, 4, 5, 6, 7, 8. And then I'm going to see what is my R to R, which at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? And then you're going to do it for the next ones. Okay? So then we're going to look at your interval practice on a normal sheet. So you'll notice the ones that we just looked at, they were zoomed in a lot. On a normal sheet, this is what you're looking at. Remember, one big box is 0.20 seconds, 5 big boxes is 1 second, and one little bitty box is 0.04 seconds, which is why we're multiplying by 0.04. So I'm going to do one of these with you, and then I'm going to leave the rest to you, and you are welcome to reach out to me for any help with these. So we're looking at your, let's go ahead and label first. This is my P, this is my R, because we have no negative deflection here, right? No QS. And this is my T, and so forth. So if I want to find my PR interval, I'm going to look at that baseline, which is right here. And when does it change? Right there on that dark line. And then where is the beginning of my QRS? When does that change from its baseline? Right here. So I would say this is about 4 boxes. Let me make that one a little bit more clearer for you. So the change for the QRS is kind of midway of the 5th box. So I would say 4.5 boxes. And remember, what do we multiply times? 0.04. My QRS segment is the beginning of the QRS, which is half of that box before the before that dark line, and the end of the QRS. I'm getting about 2.5 boxes, and again, multiply times 0.04. And I messed that up. That should be a 0.4 in front of that one. My QT is the beginning of the Q wave to the ends of the T. So I see, again, that's a half a box. 5 boxes right here. 6, 7, I'd say 8.5 boxes. Again, times 0.04. And remember, your answers need to follow in the rules, and if they do not, that means it is an abnormal arrhythmia. Okay? And then your R to R interval is right before that dark line and right after it. So I'm going to count. I'm going to say that's 4 boxes, 9, 13, 14, 15, 16, 17, 18, that's 20 boxes. So then you would do also 20 times 0.04, And remember, your QT needs to be less than half of your R to R interval. All right, that's it for chapter 2. Lots of information. I apologize for not getting these videos out to you sooner, and I will upload probably tomorrow afternoon chapter 3 and chapter 4 for you. If any of you need any help, please reach out. I am more than happy to talk to you over the phone if the weather is bad, or to share a screen with you. Sometimes it just helps to hear somebody talk to you about it versus just watching these recordings and being left confused. So good luck, and again, reach out to me whenever you need. Bye.